Tonight, we will place a single photograph inside a quiet machine and follow what happens to it. The photograph shows a small red boat resting on dark water. Above it is a pale sky. There is a line of trees at the horizon, a reflection below the hull, and no written label explaining what any of it means. To you, the scene may arrive almost at once. Boat, water, distance, evening. But an artificial vision system does not begin with any of those ideas. It begins with a rectangular field of measurements, numbers arranged in rows, columns, and color channels. Before there is a boat, there are only values. Over the next few chapters, those values will become edges, textures, patches, relationships, and eventually a position inside a learned space where images and words can meet. We will also see why this process is powerful, why it is not the same as human sight, and why a change too small for you to notice can sometimes redirect the machine completely. There is no need to remember every mechanism. You can simply follow the photograph as it moves deeper into the midnight observatory. Context is waiting beside the first wall of pixels, its cyan eye dimmed for the night. Chapter 1. Before the boat exists. The photograph enters as a grid. If it is 224 pixels wide and 224 pixels high, then the system receives 50,176 positions. With red, green, and blue channels, that becomes more than 150,000 numerical values. Each value records intensity. It does not announce that it belongs to water, sky, or painted metal. The number has no built-in knowledge of objects. Its meaning depends on position, neighboring values, the way the model was trained, and the task the model is expected to perform. The image is usually resized and normalized before it reaches the main network. Normalization places numerical ranges into a form the model expects. Resizing makes the dimensions regular enough for efficient batches. These operations sound mundane, but they already shape what survives. A thin rope may disappear. A distant bird may become one ambiguous mark. A wide panorama may be cropped around its center. Human vision also samples and filters, but it does so through a living visual system with eyes that move, attention that shifts, memory that supplies context, and a body that can approach the boat. The model receives the prepared array it is given. It cannot look behind the camera unless another system provides that possibility. Context projects 3 numbers from one blue pixel. The values float without a label. Nearby pixels are almost the same shade, and together they form a smooth region. Elsewhere, red values change abruptly against black water. That abrupt change will soon become useful. An image classifier is an information-discarding machine by design. It does not need to preserve every original value forever. Its job is to retain patterns that help with an objective. If the objective is to identify objects, exact sensor noise is usually less useful than boundaries, shapes, and recurring arrangements. At this first moment, however, the network has not yet found any of them. The red boat does not exist inside the machine. There is only a field of measured light. Chapter 2. Windows moving across light. For many years, the defining tool of modern computer vision was the convolutional neural network. Its central operation can be imagined as a small window moving across the image. Inside that window is a learned filter, a compact set of weights. At each position, the The filter combines its weights with nearby pixel values and produces a response. Then it moves and repeats the operation. The same filter is reused across the image. This reuse matters. A vertical edge near the left border and a vertical edge near the right border can activate the same filter. The model does not need a separate edge detector for every location. It learns a pattern and searches for that pattern throughout the field. Early filters often respond to simple relationships: light beside dark, one color beside another, a diagonal transition, or a small texture. The network was not necessarily given the English word edge. During training, useful filters emerged because they helped reduce prediction error. The first layer produces many feature maps. One may brighten around vertical boundaries. Another may respond to red surfaces. Another may react to fine repeated texture in the water. The next layer receives these maps rather than the untouched photograph. Now combinations become possible. A red region bordered by dark lines may contribute to a curved, hull-like feature. Reflections may produce horizontal textures. The tree line may activate irregular vertical structures above a long boundary. Pooling or strided operations can reduce spatial resolution as representations move deeper. Fine location becomes less exact, while larger patterns become easier to combine. This trade is useful for classification. The boat remains a boat if it moves a little within the frame, yet every reduction also discards information. AlexNet, published in 2012, demonstrated how powerful this layered approach could be at ImageNet scale. It used 5 convolutional layers followed by fully connected layers and achieved a major improvement in large-scale image classification. Its success did not mean that vision was solved. It showed that learned hierarchies, large datasets, and GPU computation could transform the field. In the observatory, the photograph is now surrounded by translucent maps. The original colors are still visible at the center, but each map emphasizes a different relationship. Context passes a cyan-scan line across them. The boat is not stored in one place. Evidence for it is distributed across many responses. Chapter 3. From Edges to Objects. As information moves through deeper layers, the receptive field grows. A unit in an early layer depends on a small neighborhood. A unit farther inside can depend on a much larger region of the image. This allows the network to combine local evidence. A curve alone is ambiguous. Red paint alone is ambiguous. A horizontal reflection alone is ambiguous. Together, within a learned arrangement, they may support the category boat. It is tempting to imagine a tidy hierarchy in which the first layer sees edges, the next sees corners, the next sees parts, and the final layer sees complete objects. That picture is useful, but reality is less orderly. Representations overlap. Features can serve many categories. High-level semantic information may be spread across combinations of units rather than residing in one interpretable detector. The network, therefore, does not contain a tiny internal photograph with a label pinned to each object. It contains changing patterns of activation. These patterns occupy many dimensions, far more than we can comfortably visualize. At the end of a classifier, a vector of scores may represent support for many possible labels. Softmax can turn those scores into a probability distribution. The system may assign high probability to boat, lower probability to canoe, and small amounts to unrelated categories. The probabilities are conditional on the model, its training data, its input preparation, and its label set. If the correct concept was absent from training, the classifier may be forced to choose among imperfect options. If the image contains several valid objects but the benchmark expects one label, the evaluation can hide that ambiguity. This is one reason a prediction should not be confused with an observation written in neutral language. The output is the result of a learned decision system. The system asks, in effect, which available category is best supported by this internal representation. Context points toward a constellation of labels. Boat glows brightest, but the other points do not vanish. The machine's answer is not a word discovered inside the pixels. It is a choice made from learned alternatives. Chapter 4. The image becomes patches. Convolutions are not the only way to process an image. A vision transformer begins with a different rearrangement. The image is divided into fixed-size patches. A 224 by 224 image using 16 by 16 patches becomes a grid of 196 pieces. Each patch is flattened and projected into a vector. Positional information is added so the system can distinguish the upper left from the lower right. The photograph has now become a sequence. Not a sequence of words, but a sequence of visual patch tokens. Self-attention allows each patch representation to interact with others. A patch on the red hull can place weight on another patch along the hull, on the water beneath it, or on the horizon that establishes the scene. Different attention heads can learn different relational patterns. Unlike a small convolutional filter, attention can connect distant regions directly within a layer. But this does not mean the model begins with a complete understanding of global structure. Useful attention patterns must be learned from data, and vision transformers historically benefited strongly from large-scale pre-training. The original vision transformer work showed that a pure transformer applied to sequences of image patches could perform very well on image recognition when pre-trained at sufficient scale and transferred to other benchmarks. In the observatory, context separates the photograph into floating glass tiles. Thin cyan arcs connect the red center to dark water patches, then to the pale sky. The connections change softly from layer to layer. Patch size creates another trade. Larger patches shorten the sequence and reduce computation, but they combine more raw detail before attention begins. Smaller patches preserve finer structure while increasing the number of tokens and the cost of their interactions. Both convolutional networks and vision transformers transform measurements into representations. They differ in architectural assumptions and pathways, not in the fundamental fact that the model sees numbers shaped by training. Chapter 5. When images meet words. An image classifier ends with a fixed vocabulary of categories. A vision language model can learn a broader bridge between pictures and text. CLIP was trained using image and text pairs collected at large scale. An image encoder produced a vector for each image. A text encoder produced a vector for each caption. Training encouraged matching pairs to move closer in a shared space and non-matching pairs to move apart. The result is not a dictionary stored beside every pixel. It is a geometry. Images and phrases become points whose relative positions carry learned associations. Our red boat can be compared with textual candidates such as a red boat on dark water, a car on a road, or a bird in a tree. The phrase whose vector aligns most strongly with the image vector receives the best match. This structure makes zero-shot classification possible. Instead of retraining a new output layer for every task, a user can describe candidate concepts in language and compare them with the image. Language supervision is broad, but it is not neutral. Captions reflect what people chose to write, what appeared online, and which associations were common in the training collection. Some visual details are named frequently. Others are ignored. Social biases and cultural imbalances can become part of the geometry. The shared space also compresses. Two images can be close because they share objects, styles, settings, or textual associations. Similarity does not provide a complete causal explanation of a scene. Context draws a quiet axis between image and language. The photograph glides towards several phrases. One phrase settles nearest. The machine can now describe what it has encoded, but the words inherit both the power and the limitations of its learned space. Chapter 6: Seeing More Than One Thing. Real visual tasks require more than one label. Object detection asks where objects are. Segmentation asks which pixels belong to which region. Depth estimation asks about relative distance. Tracking asks whether an object in one frame is the same object in the next. These tasks use visual backbones, but their outputs preserve different kinds of structure. A detector may produce bounding boxes and class scores. A segmentation model may create a dense mask. A depth model may assign a continuous estimate to each region. The objective changes what the representation must retain. A classification model can succeed while ignoring exact boundaries. A segmentation model cannot. A system trained only on still images may recognize the boat yet fail to understand its motion across water. Modern multimodal systems can combine vision with language generation. The visual encoder provides representations that a language model can use while producing a response. The language model may describe, compare, answer questions, or reason over visible details. Yet fluent language can conceal visual uncertainty. If the visual signal is weak, the language model may complete a plausible story from learned patterns. A tiny dark shape may become a bird because birds often appear near trees, even when the pixels do not justify certainty. A trustworthy system should preserve uncertainty, inspect relevant regions, and allow verification. In high-stakes settings, visual output should not be treated as ground truth merely because the sentence sounds natural. The observatory divides into layers: boxes around objects, masks over surfaces, depth bands receding toward the horizon, and words forming above them. Context keeps one amber question mark beside the smallest shape. Chapter 7: The Picture That Changes Without Changing. Visual networks can be remarkably accurate and unexpectedly fragile. Research on adversarial examples showed that deliberately chosen perturbations, sometimes too small for a person to notice, can cause a neural network to change its classification. The altered image may still look like the same boat to us, while the model's internal trajectory moves toward another category. This happens because human perceptual similarity and model similarity are not the same metric. The model operates in a high-dimensional input space. A coordinated change across many pixels can accumulate strongly along a direction to which the network is sensitive. The lesson is not that all visual AI is useless. It is that benchmark accuracy does not describe every possible condition. Robustness depends on distribution shifts, camera properties, weather, framing, compression, deliberate attacks, and many other details. Models can also rely on shortcuts. If boats often appear with water, a classifier may use water texture more heavily than intended. When a boat appears on land, the prediction can weaken. If training photographs center objects, the model may develop a positional bias. Interpretability tools can reveal attention maps, saliency, activations, and feature responses. These are useful windows, but they are not perfect translations of the model's reasoning into human concepts. Different methods can emphasize different parts of the same decision. Context overlays two images that look identical at normal scale. Under magnification, a faint structured pattern appears. One trajectory remains near boat. The other crosses a boundary in representation space. The visual scene barely changed. The machine's geometry did. Chapter 8. Is this really seeing? We can now return to the question in the title. Does AI see an image? In ordinary language, saying that a model sees is convenient. It means the system receives visual data and produces behavior based on it. But the word should not smuggle in assumptions about awareness or subjective experience. The model transforms arrays. It can learn representations of shape, texture, objects, spatial relationships, and language. It may perform tasks that once seemed to require human vision. None of this demonstrates that there is an inner observer watching the red boat. Human sight is joined to a body, goals, memory, movement, and a continuous world. Artificial vision may receive one frame, a video stream, or sensor data within a robot. The system's capabilities depend on that larger loop. A robot that can move its camera can test ambiguity by looking again. A static model cannot. A system with memory can compare the scene with earlier frames. A stateless classifier cannot. A multimodal model can ask language to organize visual evidence, but language can also introduce plausible details that were never visible. Future systems may combine persistent spatial models, active perception, language, and calibrated uncertainty more tightly. That is a forecast, not an established destination. Better integration could make machine perception more useful without making it identical to ours. In the midnight observatory, the many representations begin to fold together. Pixel values return to feature maps. Feature maps become patches. Patches become vectors. Vectors approach words. Each layer is useful, and none is the photograph itself. Chapter 9. The boat returns to water. Before the boat returns, we can walk once more through the observatory and notice several details that are easy to miss when the transformations happen quickly. First, consider color. A camera sensor records responses through a particular set of filters. Software then converts those responses into channels. White balance, exposure, compression, and display standards all influence the numbers that reach a model. The category red is therefore not a simple property carried unchanged from the world into the network. It is a relationship among wavelengths, sensors, processing choices, surrounding colors, and learned examples. A model trained on ordinary color photographs may behave differently when shown infrared imagery, medical scans, satellite bands, or an artistic image whose colors have been rearranged. The architecture may accept the same rectangular shape, yet the distribution of values no longer resembles its experience. Successful machine vision begins not only with a powerful network, but with an honest account of the sensor and the domain. Now consider scale. The same boat can occupy most of the frame or appear as 5 small pixels near the horizon. A detector trained on large centered objects may miss the distant version. Multi-scale feature systems, image pyramids, larger training sets, and high-resolution inputs can help, but they do not abolish the trade between detail and computation. Looking more closely costs memory and time. Humans handle scale partly through action. We move our eyes, turn our head, or walk closer. A machine can also be given active control. It can choose where to zoom, which frame to inspect, or whether another sensor reading is needed. This turns vision from a single pass into a loop. Observe, decide, move, and observe again. The loop changes the meaning of uncertainty. A passive classifier can only return a distribution over labels. An active system can use uncertainty to request another view. The right action may not be to guess more confidently. It may be to gather better evidence. Context moves toward the observatory window. The original image appears at several sizes. In the largest, bolts are visible along the hull. In the smallest, the boat is only a red interruption between sky and water. The model must learn which relationships survive these changes. Another quiet detail is invariance. We often want a classifier to recognize the boat despite small translations, changes in illumination, or modest rotations. But we do not want every task to ignore every transformation. Orientation matters when reading a digit, landing an aircraft, or interpreting a medical image. A reflection of a road sign is not always equivalent to the sign itself. The useful invariances are task-dependent. Data augmentation can teach some of them by presenting altered examples during training. Architectural choices can encourage others. Yet an augmentation that is harmless for one problem can erase meaning in another. Flipping a photograph of an animal may preserve its category. Flipping a chest radiograph can change anatomical interpretation. This reminds us that visual intelligence is never simply accuracy in the abstract. It is performance under a defined set of conditions, for a defined purpose, with specific costs for different mistakes. We can also ask what the model has learned about parts and wholes. Suppose the red hull is visible, but the mast is hidden behind fog. A robust representation may still support boat by combining partial evidence. But if the model learned a shortcut in which masts were unusually predictive, its confidence may collapse. Occlusion tests reveal some of these dependencies. Covering one region and observing the output can show which evidence mattered. But even this method must be interpreted carefully. Covering a region creates a new image distribution. The patch used to hide the boat may itself influence the model. Attention maps have a similar limitation. They show weighted interactions within a particular mechanism. They do not automatically provide a complete causal story. The fact that attention is high in one region does not prove that every other region was irrelevant, or that the highlighted pixels correspond to a human concept. Interpretability is therefore a collection of experiments rather than a single transparent window. Researchers inspect features, optimize inputs that activate units, compare representations, test counterfactuals, and measure behavior under controlled changes. Each method reveals one projection of a much larger system. Inside the observatory, context opens several such windows. One shows activation strength. One shows patch attention. One shows the direction of an image vector in the shared language space. The windows overlap but do not perfectly agree. The model has one computation, while we have several incomplete ways of describing it. Then there is time. A still photograph collapses a moment. Video adds change. Motion can resolve ambiguity. The reflection moves with the water, the boat moves against the background, and a distant shape opens its wings and becomes a bird. Video models must decide how to represent both space and sequence. They may process frames, spatiotemporal patches, optical flow, or learned latent changes. The cost rises quickly because every additional frame adds visual information. Sampling too sparsely can miss a brief action. Sampling densely can make long context expensive. Memory becomes part of perception. To track the boat, a system must associate its current representation with earlier ones despite changes in position, scale, and lighting. The identity is not stored in one pixel. It is maintained through a chain of correspondences. This temporal view brings artificial vision closer to an agent operating in a world. Yet it still does not guarantee common sense. A model can track an object without understanding ownership, purpose, danger, or the social meaning of a scene. Those broader concepts require additional experience, supervision, and interaction. Language can supply useful abstractions. It can name relations such as behind, approaching, reflected, or partially hidden. But language also summarizes. A caption rarely lists every visible fact. Training from captions teaches the model what people tended to mention, not an exhaustive inventory of reality. Imagine 10 people describing the boat photograph. One writes a red boat at dusk. Another notices the calm water. Another mentions loneliness. Another identifies a specific design. The image is the same, but each caption selects a different aspect. A vision language model learns from this uneven field of attention. At large scale, the field becomes broad enough to support remarkable transfer. It also preserves ambiguity, stereotype, and omission. Responsible evaluation must ask not only whether image and text align on average, but where the alignment fails and who bears the cost. Dataset construction therefore belongs inside the story of sight. Categories are chosen, examples are collected, labels are written, disagreements are resolved or hidden. A benchmark turns this human process into a numerical score. Some apparent model errors are actually ambiguous labels. Some apparent successes come from background cues. A rising benchmark number can reflect genuine progress, changes in data, or a model becoming especially adapted to the benchmark's habits. Careful testing uses multiple datasets, distribution shifts, robustness checks, and human review. For a deployed system, monitoring continues after release because the world changes. Cameras change. Environments change. People adapt their behavior. The visual distribution encountered tomorrow may not match the one used in training. Context dims the scoreboards and leaves only the photograph. This is a useful gesture. Metrics matter, but they are summaries. The final question is whether the system behaves reliably in the situations where people use it. Finally, consider generation. A model that creates images reverses part of the journey. It begins with a learned representation, noise or tokens, and produces a field of pixels. Recognition and generation can share visual knowledge, but they are not mirror images in every detail. A generated picture can be visually convincing while violating physical structure. It can reproduce common arrangements and fail on rare ones. It can place a red boat on dark water because that combination occupies a familiar region of its learned distribution. The ability to generate does not prove that the model has built a complete causal simulation. It shows that the model can produce samples consistent with many learned regularities. Testing deeper understanding requires interventions, predictions, spatial consistency, and behavior beyond appearance alone. One possible future combines recognition, generation, action, and memory. A system might predict how the scene will change, choose a viewpoint, compare the prediction with a new observation, and revise its internal world model. Such a system would not merely label the boat. It would use vision as one part of an ongoing relationship with an environment. That future remains incomplete. For tonight, the simpler journey is enough. Light became numbers. Numbers became structure. Structure approached language. And every step depended on choices about what to preserve. The red boat has completed its journey. It entered as more than 150,000 channel values. Convolutional windows searched for local patterns. Deeper layers combined evidence across wider regions. A transformer divided the image into patches and allowed distant pieces to interact. A vision language model placed the resulting representation near learned phrases. At every stage, information was transformed and some information was discarded. That is not a defect by itself. Useful perception requires selection. The important question is whether the selected structure supports the real task and remains reliable when conditions change. The machine did not discover a tiny word boat hidden in the red pixels. It learned a path from measured light to a distributed representation, and from that representation to an output. This path can be powerful. It can search enormous image collections, assist with scientific data, guide robots, organize photographs, and connect visual patterns to language. It can also inherit bias, miscontext, depend on shortcuts, and speak with more confidence than the image deserves. So when we say that AI sees, we are naming a family of transformations. Pixels become features. Features become relationships. Relationships become choices. Context releases the final patch tiles. They drift back into their original places. The red hull reforms, the dark water settles, and the pale sky returns above the horizon. For the machine, the image can now become quiet. The filters no longer move. The attention arcs fade. The shared space between picture and language dims until only one cyan point remains. The boat is still resting on the water. And for tonight, nothing more needs to be recognized.